Hi, everyone, and welcome to the first live Gen Chem session of 2025. My name is Corinne. I run Chem with Corinne. I am a chemistry teacher. I was a chem major way back in the day. I loved it so much. I went on to get a couple more degrees in chem, and here we are, embarrassing myself on social media to try to help as many students as possible. If you're new to Chegg is here also to just help you out. That's why they have all of these live sessions. There are 11 this week to help you out with so many of your different courses, and not just Gen Chem. Tomorrow night, there will be organic chem as well. So know that we have all of the intro level courses and some of the other courses. So definitely check out Chegg's page. If you're not following them, please do. They have so many great resources to make your life as a student so much easier. So tonight, this is just a Gen Chem session. The way this works, the more you put into the chat, the better the session is going to be. I'm going to be answering your questions live. I'm going to be just answering whatever you put into that chat. So there is no question that is too easy. There might be one that's too difficult. We're focusing on Gen Chem tonight, but I will do my best to answer whatever you put in that chat. So be sure to like and share this feed so we can reach as many students as possible. This is our first night on this many platforms, so we'll see how it goes. And the more feedback we get, the better. All right, so I thought I would get started tonight with just some rate laws and rate mechanisms, because this is something that's been a hot topic in a lot of my videos and whatnot. So let's talk through this. So what I want you to do is look at this. Our goal is to determine the overall reaction and the rate law for the following. So we're given two of those steps, and you're like, wait, why? Like, why do I even have all of this info, right? Like, where do I begin? So I think the best analogy for rates and rate mechanisms is you got to think of the overall rate as like your starting point and your end point. All right. So, like, imagine go back way back in the day when anyone was actually using Google Maps. The overall rate is like your home, right? Where you are starting and where you are ending up. All of these steps, these are your step-by-step directions to get you from point A to point B. If we have any intermediates, those are going to be our pit stops along the way. What are intermediates? Those are the things that cancel out when we're looking at all of these different steps in the reaction, the elementary steps. And then if we happen to add a catalyst, that's like your little boost. You're going to get there in a different direction, and a lot of times it's going to be a lot easier to get to your final point. All right, so let's go back to this question. So our goal is to determine the overall reaction and the rate law for the following. So what I want to do first is I'm going to go ahead and determine the rate law. So let's start there. So the rate law is basically going to tell us how fast are we forming those products. So in this case, we are only looking at the concentration of our reactants. Your products are not going to impact that overall rate law. So the rate is going to be equal to a rate constant, which is temperature dependent, times the concentration of each of those reactants. Now the question is, okay, Corinne, you have two steps there. How are we going to figure this out? The slow step is always going to be the one that determines your overall rate. So think about if you're driving on a road, and let's say it's a 2-lane road, you are stuck behind someone who is moving 5 miles under the speed limit, and there's someone right next to you making you stuck at that same speed, right? The slowest car on the road is going to determine the overall speed. And that's true for this overall reaction too. So your rate determining step is going to be the slowest step. That's going to be the one that has the highest activation energy. So we're looking at this. So we're just going to base this on the concentration of NO2. And if you look, we have two of those. So really all we have to do is just NO2 squared. Okay, so this is going to be our rate law. Now we want to determine the overall reaction. And this one's kind of easy because we just had gases. Sorry, let me back up. So that rate law, what do you not want to include in the rate law? You never want to include solids, liquids, or any intermediates, because this is just gaseous NO2. It's really easy, right? We are just going to base it on the concentration of that squared. All right, now let's determine that overall reaction. And what do I have to do? I just have to add these two things up. Think back to like Hess's law when you're doing enthalpy, when you're adding up all of those elementary steps. Same thing. We're going to cancel any intermediates that we see on both sides. So in this case, NO3 is gone. We're also going to cross out this one of our NO2s because as you can see, we see it on both sides. So now we're going to add both of those up. We're going to get NO2 plus CO yields NO plus CO2. All right, and that is it. So just a little bit of help with rate laws and mechanisms to get us started tonight. It looks like we had a question coming in about Coulomb's law. So I can talk Coulomb's law in relation to chemistry because this is a chemistry office hour. So hopefully that would help you a little bit in physics because we are going to be looking at we'll talk, yeah. So coming up next, we're going to answer that question on Coulomb's law. So thank you all for being here tonight. Again, the goal of this session is to help as many students as possible. So this is Gen Chem. So we're looking at Chem 1 or Gen Chem 2. But if you have any questions, like even a simple question, I am happy to answer that. We are here to help you. So the more questions you put in the stream, the better it's going to be for everyone. All right, so this is coming from TikTok. Can you teach me Coulomb's law in physics? I'm not going to teach it in relation to physics, but I will talk Coulomb's law. All right, what is Coulomb's law? So Coulomb's law is just this idea that the strength of the attractive or repulsive forces is related to the magnitude of the charge. So whether we're looking at something with a +2 charge or a +1 charge, the ion with a +2, like magnesium, is going to have greater attractive or repulsive forces based on the magnitude of that charge. And then the other thing that it relates to is the distance between the charges. So everything's going to be inversely related to the distance between those charges. So basically what that means is the closer the charges are to each other, think about two magnets, right? If you have two magnets that are close to each other, is it going to be harder to pull them apart? Yeah, it kind of makes sense, right? So what's nice about Coulomb's law is you can just reason your way through it. The closer those ions are, the smaller the distance, right? The stronger those attractive or repulsive forces if they have the same charge. All right, so that's just a little bit about Coulomb's law, just this idea that it's all based on the magnitude of charge. So the greater the magnitude of charge and the smaller the distance between two charges, the greater the attractive or repulsive forces. The opposite's also true. So the smaller the magnitude of charge and the further those charges are away from each other, maybe they have great, like the if so further the charges are. What do I mean by that? If we're thinking about like lattice energy, a structure, we're looking at the size of the atomic radius. So I can get more into that. I think that question was asking in relation to physics, and in chemistry, thankfully, we don't go into the details. We are just looking at the relationships between those two things. All right, I think we're going to jump over to Instagram. We had a question that came in. Can we go over chemical reactions, especially stoichiometry? Yes. All right. Let's look at chemical reactions. So everyone's going to be looking at all of the curriculum in different ways. So let's just talk briefly about the types of reactions. And let's say this might be too easy for you. Maybe you've done this for a while. We'll also talk precipitation reactions and redox reactions as well. All right. So types of reactions. The nice thing about the types of reactions is the name kind of gives away what's going on. In a synthesis reaction, you are synthesizing something, you're creating something. So let's say we'll just do a simple example, H2 plus O2 yields H2O. All right, we have combined two reactants to form a single product. This is a synthesis reaction. You can combine three reactants, and that's totally fine too. But this is just an example. In a synthesis reaction, you will have a single product because you have multiple things coming together to form that product. All right, it's going to bother me if we don't balance it. So let's go ahead and just quickly balance that. Notice we only have one oxygen atom, so we're going to put a 2 in front of that. We now have 4 atoms of hydrogen, so we just need a 2 in front of that. All right, let's do the opposite of that next. So a decomposition reaction. Think about the word decompose. When something is decomposing, it is breaking down. That's exactly what happens in a decomposition reaction. So let's say this is my favorite reaction. If you have seen this reaction, if you've ever seen the gummy bear on fire, it's thanks to potassium chlorate. It decomposes into potassium chloride and oxygen gas. That oxygen gas is what the sugar in the gummy bear then undergoes a combustion reaction with. All right, again, we have one thing breaking down into multiple products. That's how you can pick out a decomposition reaction. All right, so looking at this, again, let's balance this. Anytime you have a 3 and a 2, flip those. We'll put a 2 here, a 3 there. And then we now have 2 atoms of potassium, 2 atoms of chlorine. We just need a 2 in front of potassium chloride as well. All right, and I think I just saw another question on TikTok. Can you explain ionic versus covalent? Yeah, we will do that right after this. So we're going to continue with types of reactions, and I'll mention different compounds while we're doing that. I love to see these questions because then I can kind of connect everything so that if you're waiting on that next question, still listen in because I'll try to go over those as well. All right, next up, we're going to do single replacement. There's a chance your professor might call this a single displacement reaction. Same thing. So in a single replacement reaction, basically we have one single element reacting with a compound. After the reaction, you have a new single element. In this case, it's going to be hydrogen, and then a new compound. So you're looking for the movement and the switch between single elements. And notice, yeah, I have 2 atoms of hydrogen here, but this is a diatomic molecule. It is only hydrogen. That is still classified as a single replacement reaction. So be careful with those 7 diatomic molecules. All right, let's balance this. We need a 2 in front of HCl, and now it is balanced. All right, most complicated double replacement reactions. So in a single replacement reaction, we had a single element switching places with another one, creating a new compound after. Guess what? In a double replacement reaction, you have 2 compounds initially, and then those metal ions switch places, and then you have 2 new compounds. Let's go ahead. We're going to combine something else that we'll talk about too. All right, so let's say I have lead nitrate combining with potassium iodide. All right, in a double replacement reaction, basically what's going to happen is my lead and my potassium are going to switch places. This polyatomic ion is not going to change. It's just going to bond with potassium now to form potassium nitrate. And then whatever's left over. So in this case, it will be lead 2 iodide. So PbI2. And I don't know if anyone caught this, but for some reason I put a 2 here. This should just be Ki. So please make sure you're watching this. Make sure you are sharing this. Leave comments so we know what you need help with, because the goal with these sessions is just to help as many students as possible. All right, so in this double replacement reaction, this is not only a double replacement reaction, this is going to be a precipitation reaction. So in case you need help with solubility, looking at this, one of these will be a solid product. I want you to take a second, try to guess which one. This one's kind of obvious. So if you should know with solubility, you would want to know that everything in group 1 and any nitrate is always soluble. So this will be an aqueous solution. This is our solid precipitate. All right, so we have talked about 4 of the different types of reactions. I'm going to go ahead and clear my board. The next type you need to know is a combustion reaction. And in a combustion reaction, something is combusting, or it's going to burn in the presence of oxygen, changing all into CO2 and H2O. So we can have any type of hydrocarbon here. Something is going to react with oxygen, and it's all going to be rearranged into CO2 and H2O. So in a combustion reaction, that part is always exactly the same. The only thing that's going to change is this reactant. So that is a combustion reaction. All right, so that was all of the types of reactions and just easy ways to identify each of them. If you are working on reactions and balancing, the more you expose yourself to all of these reactions, the easier it gets. So just keep practicing. I realized I didn't even balance my double replacement reaction. That's going to bother me for the rest of the night. But what you need to do is just keep practicing with that. As you recognize those polyatomic ions in those reactions, polyatomic ions do not move, like they do not split apart. So you can track those rather than tracking individual elements. All right, so heading over to TikTok, can you explain ionic versus covalent bonds? Yeah, I would be happy to explain that. All right, ionic versus covalent. Chemistry has a lot of tricky vocabulary, and I think it's really overwhelming, a lot of these terms and things like that. But you can always use those terms. If you know the tricks, you can use prefixes and suffixes to kind of help you out. So in this case, an ionic bond, we're going to have ions. What does ion mean again? Charged particles. So in an ionic bond, we have the transfer of electrons. Okay, typically from a metal to a non-metal. All right, there is an exception. If an ionic compound has ammonium, which is NH4 plus, that is also going to act as a cation, and that is also going to transfer electrons. So even though ammonium, that polyatomic ion, does not contain a metal, it is classified as an ionic bond. All right, so in an ionic bond, we have the transfer of electrons from a metal to a non-metal. Let's do just a quick example. So like, for example, this would represent an ionic compound. So we have copper bonded to phosphate. This is a transition metal, so we would have to name it with the Roman numerals to denote the charge. So I'm going to name the first part just based on the element that we see. That's just going to be copper. I'm going to keep the name of this polyatomic ion the same as well. This is copper phosphate. And now I'm going to look back and say, okay, what is the charge on copper? So with those transition metals, remember, you have to designate the charge using Roman numerals, because with the exceptions of silver, zinc, and mercury, all of those charges can vary. So what I'm going to do is I'm going to look at my anion, my negative portion. I'm going to say, okay, phosphate has a charge of -3. Okay, so my total negative, right, for one phosphate is -3. I have two of those. So my total negative charge is going to be -6. Now I got to work backwards. I know that this part is -6. That means this half has to be +6 because a compound has to be neutral, right? So this ionic compound is going to have a net or overall charge of 0. So that means whatever my negative portion is, the metal has to be equal and opposite to that. I have 3 atoms of copper that are going to be equal to that +6. So 6 divided by 3 tells me that this is going to be copper 2 phosphate. All right, I'm going to show you a hack too. It doesn't always work, but I would say 85% of the time it does. You can also do a reverse crisscross. So if I do that, I will see that phosphate has a charge of -3, copper has a charge of +2. So know that that's an easy way to quickly determine that as well. All right, so I just talked about ionic bonds for quite a while. Let's switch gears and talk about covalent. Again, use the name. The prefix co means they are sharing. So in a covalent bond, electrons are shared. And we're not going to have any metals in a covalent bond. So electrons are shared between 2 or more nonmetals. Okay, so all of those organic compounds, anything that is on the far right side of the periodic table, if you see 2 elements that are right next to each other, it's a really good indication that it's going to be a covalent bond. So an example of a covalent molecule would be, let's just do something simple, CO2. So we have carbon bonded to 2 atoms of oxygen. This is going to be called carbon dioxide. So in covalent nomenclature, what we're going to do is we're going to use prefixes to denote how many atoms we have of each element in that compound. So if the first atom if we only have 1, we don't have to use the prefix mono. But for the second part, we're just going to add in prefixes to show how many atoms we have. CO2 is a really easy example. Let's do something a little bit more complicated. Let's do P4O10. So in this one, we have phosphorus bonded to oxygen. So this is going to be tetra phosphorus because we have 4 atoms of phosphorus and then dec oxide. So the prefix for 10 is deca. We're going to get rid of that A when we combine that with the oxide, and that becomes tetraphosphorus decoxide. Not like a with this naming system, a lot of times we'll have common names for things. So for example, water is known as dihydrogen monoxide. Do we call it that? No. But that tells us, right, that water has 2 atoms of hydrogen and 1 atom of oxygen. So just a little bit about ionic versus covalent. Let me know what else you would need help with. I have some questions about let's see, we might do some equilibrium and ice, but again, this session is all based on what you all need. we are here weekly at the same time, just to help as many students as possible, because Chegg wants to help you out and just make your life so much easier. If you haven't checked out Chegg's resources yet, I love their answers that they have. Their worked out answers, because it's not just like the answer to a problem. They explain what's going on so you can actually learn. You can learn whatever you're looking for. And even if you're like, I am so lost in Gen Chem right now that I don't even know which questions to ask, pull out your notes, put in a topic, and Chegg has so many helpful resources out there. I think what we will do, let's see. So please start putting those questions in the chat. I know we are live right now. We're live on Instagram and TikTok and YouTube. So we want to hear from you. I really mean it. That's why I'm here weekly. This is what I love to do. I love to make chemistry just easier to understand, because it can be really intimidating, as I'm sure you're feeling that. Can you explain kinetics and rate law? Yeah, so question coming in from TikTok. That's actually exactly where we started tonight. We started with rate laws and rate mechanisms. So when it comes to rate laws, just thinking like, you got to think about the analogy. It's the overall reaction is your starting point and your end point. All of those elementary steps in the mechanism, those are your directions to get from point A to point B. Any of those intermediates, those are pit stops along the way. Yes, they are in those different reaction steps, but they don't impact the overall reaction. And then if we're looking at the catalyst, that's the boost we need to make sure that we are getting from point A to point B. So there's this misconception out there that the catalyst just decreases the activation energy, because that's what you're taught in high school chem. It's not really the case, right? The catalyst is going to change how we get from point A to point B. So it's going to make sure that the reactant particles are oriented in just the right way, so that we're making sure that the reaction actually happens. We're finding a new mechanism. We're finding other steps to get there, just different ways. Yeah. All right. So that's a little bit about rate laws, and kinetics. I guess, we could do the steady state approximation, um, if that would be helpful. I don't know. Yeah. All right. We'll do another example. All right. So let's say I have these steps. So we have NO and Cl2. Sorry, let me look at my reactions. Going to NoCl2. And this is my fast step. And then my other step is going to be NoCl2. NO. Sorry, let me just get these steps written down, and then we'll talk about kinetics. Goes to 2 NoCl. Yes. All right. So let's say these are my steps that I'm given. So I have this fast reaction, and then I have this slow reaction here. So the slow step is going to be my rate determining step. Let's go ahead and write out the overall reaction here. So looking at these, we just want to add these two together, crossing out anything that we see listed as an intermediate. So in this case, the NoCl2 is going to cancel out. So we're going to have 2NO plus chlorine yields NoCl2. All right, so this is my overall reaction. I've crossed out NoCl2 because that's one of my intermediates. And now I want to figure out what my rate is, right? So I want to write the rate law for this. Again, the rate law is going to be based on that slowest step, because the slow step is going to be the one that has the highest activation energy. If we don't have enough energy to overcome that barrier, this reaction is not happening. So that's why this is our rate determining step. So the rate law is going to be based on the concentration of those reactants only, because the rate law is just telling us how we are going to form that product. So the rate is going to be equal to the rate law constant, which is going to be temperature dependent, times the concentration of those reactants. All right, simple, right? There's an issue though. So notice that NoCl2 is an intermediate. you can't have an intermediate in your rate law. So what we're going to have to do here is what's known as a steady state approximation. We're going to have to find the rate of NOCl2, which thankfully we can figure out here. I don't know why I wrote that. I should have done that. Sorry. Catching my whiteboard mistakes. There's nothing like standing in front of a whiteboard. Anyway, so I have my rate law, but I can't keep that intermediate in my rate law. So intermediates, solids, and liquids are no-nos for those rate laws. So what we have to do is we have to just find the rate of NOCl2, which thankfully, if you look at our fast step, it's easy because that's what that reaction is. So we'd say the rate of formation of NOCl2, just so I can keep track of that, is going to be K times the concentration of NO times the concentration of Cl2. So now basically what I can do to get rid of this intermediate is I can just substitute this back in to that rate law. And that's how I would figure that one out. All right, so when it comes to rate laws, you are looking at the slow step. That is your rate determining step. You're looking at the concentrations of those reactants, and you're making sure there are no intermediates, solids, or liquids in that rate law. All right, looks like we had a question coming in from TikTok. Can you explain balancing chemical reactions? Absolutely. With balancing, you got to get it in your head. You are just trying to solve puzzles, and you got to pretend. You got to fake it till you make it, right? Like you got to tell yourself, I enjoy solving these puzzles, because the more you practice with this, the easier it gets. All right, I'm going to switch markers here. All right, so tricks for balancing. We'll say balancing tricks. All right, first one, you're going to start with the element that has the highest subscript first. So let's just jump in. Let's do something tricky. Let's do a combustion reaction. All right, so let's say I have C2H6. What does a combustion reaction need? We have to react something with oxygen, and it's all going to form water and CO2. It's always the case with combustion reactions. We are burning something in the presence of oxygen, changing it all into water and carbon dioxide. All right, so with this, first hack, we want to balance starting with the element that has the highest subscript. So in this case, that's my hydrogen. So I have 6 atoms of hydrogen on my reactant side. I want to make sure I also have 6 on this side. So 6 divided by 2 tells me that I need a coefficient of 3 out in front of H2O. So anytime we put a number out here, I'm changing the number of molecules. So therefore, I'm also multiplying oxygen. But my second trick for you is that if you see something in more than 2 spots, so whether it is, like in this case, oxygen is in 3 of our reactants and products, save that for last. Because if I start balancing oxygen now, I'm going to have to go back and forth until I do not want to balance this equation anymore. So anytime you have an element that is seen in 3 or more of your substances in that reaction, save it for last. All right, so now looking at this, I have C2. I'm going to go ahead and put a coefficient of 2 out in front of carbon dioxide. Now I have to go and balance oxygen. So I'm going to look at this. I'm going to count up all of my oxygen atoms on my right side of the arrow, or my product side. I have 3 plus 4. That gives me 7 atoms of oxygen. This is another trick, especially in the beginning. You can just put, sorry, I should have put that right underneath my arrow. You can put each of the elements underneath that with the totals on both sides so you can keep track. All right, now looking at this, I have O2. Oxygen is a diatomic molecule. So I need something times 2 gives me 7. So I need 7 halves, right? Okay, if that is painful to look at, I'm proud of you, right? Like, we should not have half of a molecule. But what you can do is you can temporarily put in the 7 halves. And now I can go through and I can just put a 2 in front of this, multiply everything by 2, and this is now balanced. All right, so double checking this, I have 14 atoms of oxygen on my reactant side. I have 6 plus 8 gives me 14 on that side. And you can go through and you can check each of the elements in this reaction now, and everything will be balanced. All right, so the tricks that I just taught you, number 1, start with the element that has the highest subscript. Number 2, any substance that shows up in more than 2 places, save that for last, balance that last. All right, I'm going to show you one more trick, and then I think we're going to move into Lewis structures. All right, the other trick with balancing. Treat polyatomic ions as if they were a single element. So let's say, I can do that same reaction from earlier. We'll do something different. All right, so let's say I had, let me think. Yeah, we'll do the same one. All right. So we'll look at this precipitation reaction from earlier. So I have lead to nitrate plus potassium iodide to form potassium nitrate and lead iodide. All right, so right away you look at this and you're overwhelmed. You're like, a double replacement reaction. That means I have 4 different compounds. I have so much going on here. But what you need to do is you need to treat the polyatomic ions as if they were just a single element. So in this case, I'm going to balance my nitrates first. On the left side, I have 2 nitrates versus on the right, I have 1. I'm going to put a 2 in front of KNO3 to give me 2 nitrates now. And now I'm going to work from there. I have 2 atoms of potassium. I'm going to put a 2 in front of potassium iodide. That gives me 2 atoms of iodine, and now it is balanced. So basically what you want to do is you want to treat polyatomic ions as if they were a single element and track your polyatomic ions. Don't split this into nitrogen and oxygen. Just count your nitrates on both sides of the reaction. They are not going to split up, just going to save you a lot of time. All right. Let's see. And someone on Instagram, how to know if it's ionic? Yeah, how do I tell if something is ionic? So looking at this reaction, these are all ionic compounds. How do I know? Lead and potassium. So in an ionic compound, you are looking for the transfer of electrons from a metal to a non-metal. So with all of these double replacement reactions, these are all examples of all of these are ionic compounds. Anytime you see a polyatomic ion, that's also a quick indicator that that's going to be an ionic compound, because those polyatomic ions are also involved in these ionic bonds where we have the transfer of electrons. The other quick and easy way to look at it is if you have something like one of my favorite compounds, because I have such a sweet tooth. So looking at this one, right, this is going to be an example of a molecular or a covalent compound. I know that because it's a bunch of non-metals. Also, if you look on your periodic table, all of these are going to be, well, with the exception of hydrogen. Hydrogen's the only non-metal that's hanging out on the left side, but everything else is going to be on the far right side of the periodic table. So if all of your elements are hanging out right next to each other, chances are that's going to be a covalent molecule as well. All right. So just building off of balancing tricks. So tonight we have looked at rates and rate mechanisms. We've done some balancing. We talked reaction types. We discussed ionic versus covalent bonds. And I think we're going to do some Lewis structures next. And it looks like, oh, we also had, okay, awesome. Thank you guys. So thank you for being here. This is just a live office hour brought to you by Chegg. We will be here every week, same time, same place. And if you haven't seen yet, Chegg has 11 office hours this week. So they really want to help students. And the more you all interact in the chat, the more you share this feed, the better these sessions are going to be. So the goal is to be here to help you. So help me help you by putting more in that chat so I can answer your questions. All right, so let's see. Let's do Lewis structures. Can I do? Yeah, I can do Lewis structures. If you want to see molecular geometry, if you want to see polarity or IMF, let us know in the chat as well. And it looks like we just had a question come in from Instagram about, can I cover thermochem anytime? Absolutely. I'll plan on that after Lewis. How does that sound? All right, so let's just talk Lewis structures. So a Lewis structure essentially is just going to show us how those electrons are shared in a covalent or molecular compound. So let's say I had, I don't know, we'll do PCl3. So this is a covalent molecule. We have 2 nonmetals, phosphorus and chlorine. This is going to be called phosphorus because I just have 1 atom of phosphorus. I have 3 atoms of chlorine, so this is going to be phosphorus trichloride. So when I'm drawing a Lewis structure, there is a process to this. The first thing I recommend doing is calculating the total number of valence electrons in that compound. So to do that, so let's say, here, I have room. I'm going to write step 1, count total valence. And I'm just going to shorten electrons with the E with the negative sign. All right, so I'm going to count up my total valence. I'm going to do that by looking at the periodic table. Phosphorus has 5 valence electrons. I have 3 atoms of chlorine. Each one has 7. So 3 times 7 is 21 plus 5 gives me 26 valence electrons. You're going to do that first, and then you're going to move on. You're going to come back to that in a couple steps. So step 2, you're going to draw a skeleton structure. And in that skeleton structure, you're going to put your element that has the most positions to form bonds in the middle. And then you're going to connect that to everything else with just a single bond to start. So I'm going to put phosphorus in the middle because phosphorus has 5 valence electrons. That means it has 3 locations where it can form bonds. And if you look, we have 3 atoms of chlorine. How convenient, right? So we're going to draw in the chlorine atoms here. You don't really need to worry about how you're drawing this. I could have drawn it up here. It doesn't really matter with that Lewis structure. It doesn't have to be pretty, especially as you're trying to figure this out. It's another instance in chemistry where you are just trying to solve these puzzles. So now what I've done is I've drawn that skeleton structure. I'm going to fill in step 3, fill in electrons to satisfy the octet rule. So basically what we're going to do now is we're going to fill in the electrons on the peripheral or outer atoms to make sure that everything has 8 as it wants to have 8. So chlorine, I'm going to do 2, 4, 6 on each of these. Now if we look, each chlorine atom has the 8 electrons. It makes sense because chlorine had 7 electrons. It wanted to form that single bond. So here it is sharing a single electron with phosphorus so that everything has satisfied the octet rule. All right, step 4, you're going to double check your total. So check total. Adding lone pairs and double, triple bonds as needed. All right, so now, and this is my first time using the full board, so I apologize. Yeah, see, I can see my screen, and I'm still not including the whole screen. I apologize. You guys got to call me out on this. All right, so now what we're going to do is we're going to just look at this, and I'm going to count everything up. So I have 8, 16, 24. Just going to look at that total. That means I have 2 electrons left to place. This is kind of an obvious one. I'm just going to put those on phosphorus. All right, so now we have shown our 26 electrons. This is the full Lewis structure. Why do I care about this? Is because I'm going to use this Lewis structure to then predict my molecular geometry, right? So the molecular geometry is going to be all based on what's going on in the central atom. I have 3 bonds to that central atom. I have a lone pair that's going to take up more space than the actual bond is. This is going to form a trigonal pyramidal structure. All right, where I have the chlorine kind of coming out towards me, one behind. It's like the base of a tripod, basically. And then our lone pair up here occupying that space. And further, why do I care about the geometry? I care about the geometry because that's going to determine all of those interactions in between molecules. All right, it looks like we have a lot more people on the chat, which is awesome. Thank you guys for being here. I'm going to hop into the chat and see kind of where to go next. I think I did promise I would do some thermo next, though. So yeah. All right. Yeah. We'll do some thermo real quick. So let's move on. This is a question from Thermochemistry. Let me clear my board and we'll keep going. So if you have not been here before, this is a live office hour brought to you by Chegg. These are going to happen weekly. And this is not Chegg's only office hour. They actually have 11 sessions going on weekly right now, which is awesome. And like all of your math classes and other chemistry classes, let's say you're in Orgo, they're going to have an Orgo session tomorrow night. So Chegg wants to be there to support you. And if you haven't checked out Chegg's resources yet, they are also awesome. They are great about not only just giving you the answer, they're going to explain how you get there, which is how you learn. Especially when, sometimes in chem, it's really easy to be in a situation. Maybe you're in a lecture hall with 300 other chemistry students who are just as lost as you are, and no one wants to ask questions, right? Like, that's what this session is for. So thank you for being here, and hopefully this has been helpful so far. All right, so will I cover thermochem? Yeah, I don't know what to cover with thermochem. Let me see if there's anything else. Sorry, I'm just reading through the other questions to see if there are any related to thermo. We could just do, let's see. All right. Let's do a Gibbs free energy question. All right. Let me pull up some numbers so I have good numbers for this. All right. So let's look at this reaction. So we have silicon reacting with fluorine to yield SiF4. All right, and let's say we're given our delta H values. And our delta S values. Sorry, let me just write all of this out and then we will discuss how to solve this. All right, sorry, I should have left more space here. 2.8. All right, so let's say I want to figure out the enthalpy of this reaction under standard conditions. So these are pure substances. They're just going to have enthalpy values of 0. So when you're given a table like this, it is really easy to get overwhelmed because you look at this and you're like, wait, where do I even start? How am I going to find delta G? So what you have to remember is the Gibbs free energy equation. Delta G equals delta H minus T delta S. So we'll say we want to determine delta G at standard conditions. So, or here, why don't we just say at, all right, so determine the Gibbs free energy at 25 degrees Celsius for the following. All right, so what I need to do now is I need to remember that the delta H and the delta S, so the enthalpy and the entropy, it's going to be equal to the sum of the products minus the reactant. So what you're going to need to do is calculate those first. And you could technically put it all into this equation right away, but it's a lot easier to make a mistake when you do that. So I would calculate each individually and then plug everything back in. So looking at this, delta H is products minus reactants. This one's going to be nice and easy. It's just going to be negative 1614.9 kilojoules per mole versus our entropy. Let's go ahead and calculate that. Delta S is going to be the sum of the products, which was, okay, so that's just 282.4 minus our reactants. So 18.83 plus 202.8. What does that give us? Let's see. All right, so that gives us 60.77 joules per mole Kelvin. So be careful with this. A lot of times your entropy value is going to be given in joules, whereas your enthalpy is in kilojoules. So all you have to do is convert one or the other. I tend to just convert this into kilojoules by dividing by 1,000. So this becomes let's see, 0.0607 kilojoules per mole Kelvin. So now that I have that, I can plug that in here. I'm going to make sure my temperature is in Kelvin. So I just add 273. This is going to be 298 Kelvin. I'm going to just have my delta H, again, sum of products minus reactants. This is just negative 1614.9. And then I just solve for it from there. I don't know if that was helpful, if that was what you're looking for thermo. So please just let me know in the chat, ask very specific questions. Oh, and there is one now on thermo. I apologize. All right, so on Instagram, can you specifically cover calorimetry? Yes, I would be happy to. All right, I guess what we'll do is we'll talk like what's going on in calorimetry, right? So with thermo, you are doing a lot of calculations with enthalpy and entropy like I just did. Got to be careful with those. Most of the time you're looking at the sum of the products minus reactants, unless you're looking at the bond enthalpy, in which case it's flipped, so to be careful with that. But we can also look at calorimetry. All right, and calorimetry is going to be based all on this Q equals mc delta T, where Q is the heat, M is your mass, C is the specific heat, basically the amount of energy that is required to change 1 gram of a substance 1 degree Celsius or Kelvin, depending on the units. And then delta G is just your final minus your initial. It's your change in temperature. Anytime you see a delta in chemistry, you know you're looking at the change of something. Delta is just this triangle symbol. All right, so that is basically in calorimetry. Basically what you're going to be doing is you're going to be taking this equation, and the heat gained by something is going to be equal to the heat lost by something else. So let's say you take a hot piece of metal in lab, you drop it into a cup of water, typically a styrofoam coffee cup calorimeter. It's not always going to be the best lab data, right? But that's what everyone uses. And then you're going to measure that change in temperature to either figure out what the specific heat is or calculate the heat gained or lost. So that's just a little bit about calorimeters. Be careful with this. Be careful with your signs, making sure you're really thinking through, okay, what's going on here? Is my heat being gained or lost by the water or the metal? Be careful with your specific heat values. Make sure everything matches up with the substances that you are looking at. All right, let's see. Let me hop back in the chat and see what else. And thank you all for being here. This has been a good session. Okay, I do see there's a question on the preparation of, it looks like allenes, and maybe it was meant to be alkanes. If you're here for organic, know that there's another session tomorrow night. I don't know what the time is, but check out Cheg's page because they do have a specific, an office hour that's geared just for organic chemistry. All right, let's see. Can we discuss periodic trends? Yeah, let's do that. All right, so we have a question on TikTok. Periodic trends. We are doing a little bit of everything tonight, but that's what these sessions are made for, okay? And what's really nice is now that we are streaming on so many different platforms, I think the goal is to be able to share these. So if I go through something and you don't see, like you missed it, like for example, I had done rate laws right in the beginning, know that you can go back and hop back on and watch these as well. All right, so we're going to talk periodic trends, and it looks like I have a request to do molarity, and I will do that next. All right, so periodic trends. Where do you need to focus when it comes to the trends? You have so many trends you have to memorize, right? Like, how do you do it? You don't. All right, what you're going to do is you're going to focus on, look at my wonky periodic table here. You're going to focus on knowing one trend really well, and know that everything else is based on that. So let's look at atomic radius. Sounds so fancy, right? What is atomic radius? It's essentially the size of the atom. So relative distance from nucleus to outer edge of the electron cloud. All right, so that's a fancy definition. What is it? Size of atom. All right, so when I look at the periodic table, as I move down a column, what's happening? I'm adding energy levels, right? So as I move down a column, the atom gets bigger. It makes sense. As I'm adding more to my electron cloud, I'm going to make this really over-exaggerated so you can see it. As I'm adding energy levels to the cloud is getting bigger. Therefore, the size of the atom is increasing. That makes sense. Now, this part across periods does not make sense. So this is the tricky part, but I promise you can pick it up. As I move across a row or a period, I am not changing the energy levels. What I am doing is I'm adding more protons to that nucleus. Okay, as I add more positively charged protons, the strength of that magnet, per se, is getting greater. Okay, so as I add more positively charged protons to the nucleus, those electrons are like, whoa, I really want to get closer to that positive charge. So the greater we call it the effective nuclear charges, or the amount of positively charged protons in the nucleus, the more the electrons are pulled in towards that nucleus. Therefore, the smaller the atomic radius. So as I move from left to right, my atomic radius actually decreases slightly. So that's all based on the nuclear effective charge. So again, as I add more positively charged protons to the nucleus, the stronger those electrons are attracted towards the nucleus. This is known as Coulombic attraction. And then the term here is effective nuclear charge. So basically the size of the atom shrinks as I move left to right. The greatest atomic radius is going to be francium. All right, now thinking about the other periodic trends. So let's say you need to know ionization energy. So we'll do ionization energy in orange. All right, so ionization energy is the amount of energy needed to remove an electron. One of the, typically we look at first ionization energy, which is the outermost or valence electrons. What makes sense? Would it be easier to remove an electron that's further away from the positive nucleus that it's attracted to, or from one that's closer to the nucleus? Think about that for a second. It takes a lot less energy to remove something that's further from the nucleus. There's less of that attractive force. This is going to have the lowest ionization energy. And then the smallest nucleus is going to have the highest. Okay, because the smallest atomic radius, the smaller that atom is, the closer those electrons are to those positively charged protons, and therefore the harder it's going to be to remove them. All right, so that's ionization energy. Electronegativity is going to follow that same trend. We can look at ionic radius, we can look at electron affinity, but what you always want to do is go back to atomic radius. Everything's going to be based on that. It's going to be based on Coulomb's law and based on that effective nuclear charge. All right, just a little bit about periodic trends. Looks like we're going to move into molarity next. So we have some questions coming in from TikTok, and that's where we're going to go next. So thank you all for being here. Please do us a favor, share this feed. I'm going to be here same time next Monday night, and I'd love to hear what you all would like for me to cover. I was ready to do like ice and equilibrium tonight. It seems like that's not what you all need. So thank you for being active in the chat and for letting me know. We're going to switch gears and we're going to do some molarity now. And molarity is intimidating when you first start. So when you're doing molarity, you need to know the equation. I don't know if this orange is showing up. Okay, awesome. So molarity is a capital M, because we don't use enough M's, and moles in chemistry is equal to the moles of solute per liters of solution. All right, so basically molarity is equal to the moles per liter. You might also see it as molarity times volume equals moles. So it's also a really useful version of this equation. It's just the same equation, just rearranged a little bit. So know that those are the same thing. So basically, if I take a solid substance and I dissolve it in water, the molarity is going to tell me my concentration. So let's just do an example. So let's say I had, I don't know, 15 grams of sodium chloride, and I dissolve that in a volumetric flask. I bring that to a volume of 200 milliliters, and I want to find my concentration. So I'm going to put my solid into, well, I'll draw a little volumetric. Whoop. I then fill to my volume. I've never heard of a 200 milliliter volumetric. I don't even know why I said that. I fill it to this mark, and then I want to find my concentration. All right, so what do I need to do? I need to convert this into moles first. So you always want to make sure your solute is in moles and your volume, your total volume, or your solution volume is in liters. So let me just write this out. Sorry, not my best wording for a practice problem, but you guys get the gist of it. So what we want to do is we want to then just convert from grams into moles. We're going to divide by that molar mass. Sodium chloride, I normally would know this off the top of my head. It's 58. Okay, so I just found the molar mass of this by adding up my sodium and my chlorine. I divide, and then I get my answer in moles. So this is 0.257 moles of NaCl. All right, so I've changed my mass into moles of solute. So I have that first part. So this is 0.257 moles. And then I just want to convert my milliliters into liters. So to do that, I'm dividing by 1,000. A couple ways to do that. You can actually divide, or you can just move your decimal 3 places over to the left. This is going to be 0.200 liters. Then all I have to do is just divide. So 0.257 divided by 0.2 gives me a concentration or a molarity of 1.285. I'm going to round that up to a 9 to make sure I have the 3 sig figs that I had in this initial value. All right, so of course, so now equilibrium comes into the chat. So what we will do is I will plan. I had a lot of questions ready for equilibrium and ice. I will plan on doing that next Monday. That's what I will start this session with. But please know that there's going to be another Gen Chem session on Thursday. So check out Cheg's different social pages. They'll have all of this, a full schedule. Like I said, they have 11 of these sessions. They're just here to help you out. So hopefully that was helpful with concentration. I don't have enough time to go through equilibrium, but I'm going to plan on doing that. We'll start with like a nice ice table and just look at that. And then I will probably release a video this week as well on KSP and equilibrium. All right, let's see. Can I help with finding the excess reactant and how much is used in a reaction? Yeah, and I will make sure I have another question prepped for that too. We can talk through it though. So from TikTok, could you please help with finding excess reactant and how much is used in a reactant? I will tell you the most common mistake with excess and limiting reactants is looking at the mass or the moles of reactants and then trying to take a guess as to which one is the actual limiting reactant. You cannot do that. Okay, so with the limiting reactant, what you need to do is you need to make a prediction about how much product each is going to make. So the limiting reactant is based on which reaction is going to limit, which reactant is going to limit the overall reaction, right? So if it's the limiting reactant, it's going to be the one that forms less product. So pick one of your products in that reaction and then just do some stoichiometry really quick with each of those reactants, see which one makes less product. That will determine your theoretical yield. And if you want to figure out how much is used up in a reaction, then what you need to do is take that limiting reactant, do some stoichiometry where you then figure out how much of the other reactant you need to react perfectly with that reaction. I don't know. I have 2 minutes. I feel like I could almost like go through an example of that. I don't know. We'll just do something simple. I don't know. See, this is a problem. It's hard to make up problems on the spot with chem. But basically with limiting and excess reactants, you need to just do some math, right? Just do stoichiometry. You don't have to go all the way to grams. Just look at moles. Pick one of your products, figure out what that's going to be, figure out which one makes less product. Whichever reactant makes less product, that is your limiting reactant. All right, we had one more question coming in from TikTok. Can you explain the preparation of alkenes? No, I cannot, but tomorrow night there is an organic session. So this session now, if you were here in the fall, we were doing a little bit of everything. We were doing Gen Chem, some Orgo, some P-Chem even. But what Chegg wants to do is make sure that each session is specific to the class that you are in. So come back tomorrow night and you will have an hour-long organic session. So please bring that question back tomorrow night. Yeah, so thank you all for being here. I hope this was helpful. Please share this and know that I will be back next week. And yeah, so another question on TikTok. How can I memorize the solubility rules easily? Focus on what is always soluble. So look at group 1, nitrates, acetates. You can also remember the mnemonic device, PMS Castro Bear. I know Chegg has a video on their TikTok page that goes through this. It's really helpful. So yeah, so just make sure that you are, okay, there we go. Tomorrow, Professor Dave Explains will be here for an organic session. So please come back for that. Yeah, and when it comes, like I said, solubility rules, focus on what's always soluble. The exceptions are going to be PMS Castrobare. So we're looking at lead, mercury, and silver, and then also calcium, strontium, and barium in the presence of sulfates. So just a little bit about that. So thank you all again for being here. Please give us some feedback using that feedback survey, and we will see you same place, same time next week.